sir.
Thank you. Let me share my screen. I just would like to ask whether you can see my screen.
Yes, sir, it is visible.
Okay.
Yes.
Okay.
Just,
thank you. Okay. Should I
just
start?
put it in presentation mode.
Okay. Yeah. Sure. I think it's okay.
Yes, sir.
Okay. Okay. So good morning, everyone. Although it's close to 1 a.m. here in US. But anyway, so thank you for inviting me to give a talk on my research area. Today, I'll briefly discuss about the material platforms for quantum photonics and quantum information science, where I'm working for the last couple of years. So in the outline, I'll discuss about the introduction, where I'll discuss about the future prospect of quantum computing. It is relatively a new area which is yet to be unveiled in detail, and a lot of exciting features are there as we go deeper. So if you are a student and listening this talk, you may be, from physics background or electronics background or electrical, computer science, material science, whatever it is. I just would like to tell you that lots of opportunities are there for you in coming future to pursue your career in this field, like artificial intelligence, machine learning, and Internet of Technology, what are booming right now. Recently, I even found one paper where they have shown how machine learning could be merged together with quantum photonics. So lots of opportunities are there, especially in this quantum photonics. Talking about this materials analysis, well, folks are doing research on several materials, and among them, diamond, silicon carbide, nitride materials like gallium nitride, hexagonal boron nitride are noteworthy. Now, diamond is really very fascinating due to the presence of nitrogen vacancy center. And finally, I'll discuss about the summary. So this is the IBM's 53-qubit quantum computer, which has been launched just last year, I think in January, in 2019 January. So if you think that 50 years ago, even smartphones would have been the ultimate computing wizardry, just as classical computers were almost unimaginable due to, for the previous generations. Now we are now facing the birth of an entirely new type of computational system. So if the word quantum makes your head spin, so you are not alone, because this is a very small, very cold, very sensitive, and very weird system for which Apple, Google, and Rigetti computers and so many researchers across the globe are actually working day and night to make it successful. So what is this qubit? So quantum computer actually process qubits unlike binary bits in classical computers. So if you just think in terms of classical computer, whatever you see in classical computer, be it text, images, movies, these are nothing but large strings of zeros and ones. But in quantum computer, there is no binary. They actually process this qubit. So what is this qubit? So if you think you are tossing a coin, either you'll have 1 or you'll have 0. That is your binary bits, and that is the logic where your classical computers work actually. But qubit is nothing but a spinning coin. So simultaneously you'll have 0 and 1. So just think about the processor speed, how much it will be. So for a complex algorithm or complex calculations, if classical computers take, say, millions of years, quantum computers can process it within a couple of hours, because the processing speed will be extremely high due to this qubit. But to realize this sophisticated system, you need cryostat, because whatever this machine you can see right now, this is not operatable at room temperature. This can be operated at cryogenic temperature. Now, cryogenic temperature is only 4 Kelvin, where your room temperature is 300 Kelvin. So you need a machine. You can see this is a cryostat which was found in Google's lab. Just think about the size of this cryostat and the cost per month the company has to actually take care for taking care of the whole system. So this is extremely costly right now. So everyone is looking for room temperature quantum computing system, which is still under research, and no one has reported. So apart from this quantum computation, I'll also discuss about some other applications of my research, which are quantum radar, and of course, quantum sensor, because our Air Force, US Air Force is actually desperately looking for this kind of quantum radar and quantum sensor, because China has already invented quantum satellite, which is unhackable. So in order to increase the strength of your defense, Navy and Air Force, US is actually desperately looking for such kind of sophisticated technology. So we have actually large number of collaborators who are actually working with us. Obviously, from my country, we have collaborated with my alma mater, IIT Bombay, where we are working with the physics department and Professor Bibhas Saha from JNCSR, Bengaluru. In US, we have multiple collaborators starting from the East Coast. So we first collaborate with our Department of Physics, Ohio State University. Then from the same state, but in a different city, Dayton, we have our Air Force Research Lab, with whom we are also working for hexagonal boron nitride material platform. We also got connected with University of Michigan, Ann Arbor, where we are actually working in the nitride platform, especially nanowire and quantum dot. Then in New York, we have Rensselaer Polytechnic Institute, who are actually doing theoretical investigations of the defects which are found in the materials. We also have Naval Research Lab, who are working with, again, hexagonal boron nitride, but what kind of defects are responsible for getting single photon emission. Dr. Vikramaratne is working with us from Naval Research Lab, which is in Washington, DC. In Oklahoma University, we have Professor Gerg, who are working with for the thermodynamics research in hexagonal boron nitride. Mainly, they are actually our theoretical collaborator, except University of Michigan. And here you can see from New Mexico, we have a Sandia National Lab. And finally, from the West Coast, we have University of California, Santa Barbara, a very prestigious institute across the globe. So they are also working with us. So you can see we have multiple collaborators with whom we are working day and night. Now, the question is single photon. We are actually looking for single photon emission. Now, you know what is photon, because photon is defined as an elementary excitation of a single mode of the quantized magnetic field. And the concept of quantized electromagnetic radiation was first introduced by Planck in 1900 to explain the black body radiation. Then in 1905, it was also used by Einstein to explain the photoelectric effect, for which he got the Nobel Prize. And finally, in 1923, Compton also described this, the scattering X-ray effect. But the term photon was introduced by G. N. Lewis in 1926. Now, you might ask me why we are looking for single photon. What is the beauty of single photon? Because of the explosive growth of quantum information science over the last few decades. At its core, so the point is, what is ideal single photon? People are talking about single photon, but to achieve this ideal single photon, it has not yet been reported. When I'm talking about ideal single photon, it means only one photon will be generated. What do you mean by it? Because when you think about photon emission, it means multiple quantum packets are actually transmitted, but not the case. That you have to ensure you are actually allowing only one photon. So multi-photon emission should be reduced at any cost. It's very difficult to achieve, but that is the criteria for getting ideal single photon emission. Number two, no blinking and bleaching. And room temperature operation, you have to ensure to reduce the cost. because every time you can't operate a machine at cryogenic temperature. That would cost huge. Sharp ZPL or zero photon length is also necessary because maximum photons are actually generated in this spectrum. So zero photon length is extremely important to ensure whether you are getting ideal single photon emission or not. Another important property which ensures ideal single photon emission is entanglement. What is this entanglement? You can see two particles are here. So it's a kind of spooky action. Why I'm talking about spooky action? Because if the two states of a quantum particle are separated far away from each other, but if one state is perturbed, another state will also be perturbed, no matter how far they are from each other. So that is the beauty of entanglement. They might be separated far away from each other, but if one state is perturbed, another state is bound to be perturbed. And this property is known as quantum entanglement, and very important property to ensure ideal single photon emission. So what are those materials from where single photon emission has already been reported? And among them, you can see single atom. That is the first platform from where single photon emission was reported. What I remember, it was probably sodium. Then you can see SPDC. This means spontaneous parametric down conversion. NV center, nitrogen vacancy center. QD, that is quantum dots. Apart from that, you have to take care about the tunability. What do you mean by tunability? Tunability means what is the range of your wavelength spectrum, how far your single photon can go. For single atom, it is very less, just transition lines. For SPDC, well, it's quite big. You can see from visible spectrum to more than telecom wavelength. For nitrogen vacancy, it's very narrow, only 600 to 800. Again, it is confined only in visible spectrum. But for quantum dots, 600 to 1550 nanometer. 1550 nanometer is the telecom wavelength. Now, what about the second property, coherence? Now, many proposed schemes of quantum information science require scalable quantum emitters capable of producing indistinguishable single photons or entangled photon pairs. Now, to realize such quantum emitters, you have to ensure whether your optical coherence time is exactly 2 times of the spontaneous emission lifetime. If not, then there is some problem with the coherence. Even your coherence gets disturbed with the presence of phonon scattering, spin noise, charge density fluctuations. What is the purity? What do you mean by purity? When I'm talking about purity, I actually mean whether it is multiphoton related or it is single photon. So if multiphoton emission is there, that purity can be measured by the second order correlation factor G2. The instrument which is used to measure this purity is known as HBT, or Hanbury-Brown twist interferometer. The closer it is to 0, the better the result. So you can see from this table, quantum dots 0.000075. It is very close to 0. So quantum dots is again getting the highest point in terms of purity. Scalability is another important, because whatever device you design, you realize if it is not scalable, then you can't sell it in the market. So if there is no commercialized value, your product is of no use actually. Apart from that, emission direction, emission rate, entanglement fidelity, efficiency, and integrability, all these parameters you have to take care while realizing single photon emitters. So we are actually currently focusing on hexagonal boron nitride. You can see this hexagonal structure where boron and nitrogens are actually bonded with each other. And this is the material what we have deposited. So you can see HBN thin films were deposited on HOBG, or silicon carbide substrate. HOBG is highly oriented pyrolytic graphite substrate. I repeat, highly oriented pyrolytic graphite substrate, or silicon carbide substrates. We are also thinking about to deposit our HBN thin films on sapphire substrates also. Because to get the single photon emission, you also have to take care about the contribution of your substrate. If your substrate has highly absorbance coefficient, then that would be of no use, because whatever photon you can generate, that will be absorbed by your substrate. So you have to take care about this substrate. Unfortunately, HOBG may be a good substrate for getting large scale of HBN thin films, but it's not good for getting a single photon emission because graphite will absorb. So why HBN is so interesting? So HBN is fascinating because its emission, it can emit in both visible and UV regions. It has very high brightness and controllability of emission. Point defects in HBN are responsible for single photon emission, but whether it is nitrogen vacancy or boron vacancy, that has not yet been proved so far. Every day you'll find a new paper and they are arguing with each other. Recently, I found one paper where they have provided that carbon vacancy might be the reason for getting single photon emission, but still, it is still under debate and no one has proved it experimentally. Until and unless you get some result experimentally proved by some group, then debate will continue. HBN is also called white graphite. So I can show you one more figure. You can see these all are actually two-dimensional structures. You can see graphene, you have HBN, MOS2, there's a molybdenum disulfide, WSO2, that is tungsten diselenide. So HBN is also known as white graphite, and it's a van der Waals materials, which means that in-plane bonding is very, very strong compared to your outer plane bonding. And one of the most interesting feature of this HBN that if you grow only one monolayer of HBN, you will see it has a direct band gap. Okay, keep growing this layer, then you will end up, when you will end up with bulk HBN and measure the band gap, you will find it is indirect band gap. And this indirect band gap has been found so far 6 electron volt. And this is this platform is an excellent for getting single photon emission. So apart from gallium nitride, apart from HBN, we are also working with gallium nitride. Now we can see in figure B, this is gallium nitride core shell, algan GaN. Algan has higher band gap, so algan is working as the cell structure, which is actually protecting the inner gallium nitride. And there is another gallium nitride quantum dot. So quantum dot will actually emit the single photon emission. Apart from that, in bottom in figure D, you can see that people have also worked with GaN in-GaN nanowire quantum dot, where your in-GaN will emit the single photon. Even if you can see the figure C, you can see this algan are actually working as a barrier, while your GaN is actually the core structure. So apart from HBN and GaN, people are also working with this gallium arsenide quantum dot and gallium arsenide phosphide and nanowire. So this kind of structures are also there. But why we are looking for quantum dot for single photon emitter? Because quantum dot is a 0 dimension. As you know, nanowire is 1-dimensional, quantum well is 2-dimensional, bulk material is 3-dimensional, but as quantum dot is 0-dimensional, so it has very high exciton confinement energy, due to which it will have very high emission rate, narrow emission line width, and high fidelity anti-bunching. But while growing this quantum dot, you have to make sure that what kind of quantum dot you are actually growing, because if it is Transky-Krasnov or SK quantum dot, then site fluctuation can occur. Colloidal quantum dot is responsible for blinking. So you have to think about the tapered-shaped nanowire quantum dot, where you must ensure that whether you are getting symmetric quantum dot or not. Otherwise, if site fluctuation is there, then spectral diffusion will be there. When spectral diffusion is there, then your intensity will be reduced. And so what are the best platforms compared to this gallium arsenide phosphide is good, or gallium nitride? I mean, nitride-based platforms are good. So definitely my choice is nitride quantum dot, because in nitride quantum dot, you will have lots of opportunities to explore the wavelength spectrum, because your aluminum nitride is 6 electron volt, gallium nitride is 3.4 electron volt, indium nitride is 0.65 electron volt. So in nitride platform, you have a huge opportunity to tune the wavelength. At the bottom, I have shown another graph where I have shown the purity of the single photon emitter of this gallium arsenide phosphide and gallium arsenide-based nanowire quantum dot. So you have nanowire and you have quantum dot. Now your quantum dot can emit single photon. You learn it. So what are the process through which you can emit this single photon from quantum dot? Obviously, you have to provide some external power through which you can get this single photon. So one source is optical pumping. So you provide some laser pulse, you excite this quantum dot, and from quantum dot, you'll get single photon. Another platform is electrical injection. So you can see this is a PIN layer. P layer is at the bottom, intrinsic layer is at the middle, and finally you have N layer. So you make a forward bias, and from the NV center, you can get a single photon emission. So there are two options, optical pumping and electrical pumping. At present, my group and myself working for the optical pumping, where we'll just pump this quantum dot through some photoluminescence measurements, and we'll excite this quantum dot to get a single photon emission. So what are the instruments we in our group are actually using? So this is our growth machine. Now, whatever I have discussed so far, like gallium nitride or InGaN or HBN, like hexagonal boron nitride. So these materials we actually grow in MBE. So this is the total structure of the molecular beam epitaxy. This is a very good instrument for getting high quality, high crystal quality of your samples. The vacuum you'll get in the order of 10 to the power 10 to 11 torr, and the temperature is around say 800. In our case, we get around 1000 degrees centigrade. There is another system through which you can grow this kind of materials, and the temperature is extremely high, like 1700 degrees centigrade. That is called MOCVD. But we are not using MOCVD because if temperature is extremely high, then controlling layer by layer structure will be very difficult. And most importantly, at a high temperature, indium will start to phase segregate. Once it is shows this kind of nature, then getting symmetric indium InGaN quantum dot will be very, very difficult. So at the same time, you have to ensure whether you are getting high vacuum, and you also have to ensure whether you are getting that opportunity to control the growth of your material. So these two criteria you have to fulfill. So this is another system what we are using here right now. This is atomic force microscopy. This is a very good instrument for getting the result of structural quality of your system, what kind of texture you are getting, whether your surface is smooth or rough, what is the thickness, and what is the grain size of your sample. Every information you can gather from atomic force microscopy. So this is XPS, or X-ray photoelectron spectroscopy. So whenever you grow any material, for example, I'm growing boron nitride. So it's not like that you'll only have boron and nitrogen in your system. You might end up with several impurities, and these omnipresent impurities are always there whenever you grow any materials. Like it could be carbon, it could be oxygen, it could be sulfur. So what about these impurities are present here in your material? You can easily measure through XPS, and they will show the exact content. What about the percentage of those impurities are present in your sample? Apart from that, we are also using this X-ray diffraction, which will give you another confirmation about your structural quality, whether your film is single crystalline or polycrystalline or amorphous. Everything can be ensured through this X-ray instrument. This is X-ray diffraction. We are also using photoluminescence measurement. As I told you, for optical pumping to excite your quantum dot in order to get single photon emission, you have to use this photoluminescence setup. And this is another setup which is SIMS, that is secondary ion mass spectroscopy. So if you would like to intentionally incorporate some material in your film, for example, if you would like to dope, then what is the doping concentration you can also measure with the help of this SIMS, which can ensure what kind of doping concentration are there in your film. So this is our group, and at the right-hand side, this is our consolidated instruments with which we are working day and night. Thank you.